This is a video about how one thing can be described in two different ways. Specifically, it's about two theories, music theory and group theory. I want to show you that some of the most elementary concepts in music theory can be described in the language of group theory. If you don't know much about music theory or group theory, don't worry. You shouldn't need to know much about either of these things in order to get something out of this video, although it's going to be a lot of information. A lot of this information is derived from a paper called Musical Actions of Dihedral Groups by Alyssa S. Kranz, Thomas M. Fiore, and Ramon Satyendra. If this topic interests you or you have a mathematical background, I would recommend taking a look at this paper as it's much more technical than the material in this video. I'll link the paper below. Let's start with groups. Let me provide some examples before we consider a formal definition. Consider a square, which is a regular polygon with four sides. Suppose we assign each vertex a number 1 through 4. How many ways can we transform this square so that there are still vertices in all the same places? By transformation, I'm referring to combinations of rotations and reflections. As it turns out, there are 8 ways of transforming the square. We can rotate it by 0, 90, 180, and 270 degrees before we get back to the 0-degree rotation. Or we can first reflect the square over an axis and then perform the rotations. If you don't believe that these are all the transformations, it's pretty easy to try for yourself. Together, these transformations form a special type of group called the dihedral group D4. Actually, any regular polygon with n sides has a group of symmetries called Dn. These groups are called the dihedral groups. Here's another group. Consider the 12 integers 0 through 11. These integers also form a special type of group called Z mod 12z under an operation called addition modulo 12. Addition modulo 12 is just like the addition most people are familiar with, but after adding two numbers, you subtract off any multiples of 12. For example, 4 plus 4 equals 8 modulo 12 because 8 is not larger than a multiple of 12. 10 plus 8 is 18, then we subtract 12, so we say that 10 plus 8 is 6 modulo 12. 6 plus 6 is 12, we subtract 12, so 6 plus 6 is 0 modulo 12. You can think about it like this. Instead of the numbers forming a number line, they form a number circle with 12 numbers on the edge. So, what actually is a group? Here's the mathematical definition. A group is a set, really just a collection of mathematical things, with an operation that exhibits certain properties. The operation is called a binary operation, and it's a way of combining any two elements of the set so that you receive something that is still an element of the set. Like how the symmetries of a square can be combined into something that is itself a symmetry of the square, or how addition modulo 12 takes integers between 0 and 11 and produces an integer between 0 and 11. The group operation is often called addition or multiplication, but it can be any operation that behaves correctly. For example, on D4, the operation is function composition. For more mathematical viewers, groups also have to have the following properties: associativity, an identity element, and an inverse element for each element. Now let's talk about some music theory. There are 12 pitches or notes in the Western scale. Consecutive notes are separated by a half step or semitone. Humans have long recognized that two notes, which are 12 semitones, aka 1 octave apart, sound alike. So the notes that are a multiple of 12 semitones apart are referred to as the same note, but in different octaves. We call these the pitch classes. Melodies are formed from these pitches. Sometimes a melody is shifted up or down into a different register. This is called transposition. Under a transposition, every note is shifted up or down by the same number of semitones. Another common technique is inversion. Inversion is an overloaded term in music. It can mean multiple things depending on the context. In our context, it means that the pitches are reflected around a root pitch, typically the first pitch in a melody. Specifically, this is known as a melodic inversion. This technique is used very overtly in works like the Fugues of J.S. Bach. As it turns out, we can liken the 12 pitch classes to the integers modulo 12, Z mod 12z. We can say that C is 0, C sharp is 1, D is 2, and so on. By arranging the pitches, or their corresponding numbers, around a regular 12-gon, we form the musical clock, or pitch clock. This shape has symmetries. In fact, the group D12 can act on it by transforming it, which rotates the clock or reflects it over an axis. This is precisely the same as a transposition or inversion of the notes on the clock. This is an example of a group action, which is when a group acts on a set. In this case, D12 acts on the pitches by transposition and inversion. Here, the set, Z mod 12Z, happens to also be a group. This is a good time to introduce another group theory concept, isomorphisms. When two groups share the exact same structure, we say that they are isomorphic. In fact, the two groups are the same group, despite the fact that the elements might have different names or that the group operations are described differently. We can see that D12 is isomorphic to the transpositions and inversions of the 12 pitches, which we refer to as the TI group. As a word of warning, from this point, things are going to get more technical. Our next discussion hinges on the concept of a triad, specifically a consonant triad. These are the major and minor chords in their simplest forms. A triad consists of 3 notes: a root note, the third, which can be 3 semitones above the root for a minor chord or 4 semitones for a major chord, and finally the fifth, which lies 7 semitones above the root. Triads are so ubiquitous in music that it's difficult to imagine music without them. The major triads are denoted with capital letters, and the minor triads with lowercase letters, so capital C is C major and lowercase c is C minor. Note that because the TI group acts on the pitches, it can be said to act on the triads, where the transposition or inversion is applied element-wise to the notes in the triad. In keeping with the convention used by crayons in the paper, 0, 4, 7 is the C major triad. It could be inverted around C, the root, into 0, 8, 5, which is an F minor triad. We can really nicely represent the action of an element of the TI group on a triad using the pitch clock. The parity of a consonant triad is whether the triad is major or minor, and swapping the parity turns a major triad into a minor triad and vice versa. There are 12 pitches, each with a major and minor triad, so there are 24 consonant triads. Note then that the TI group in the context of consonant triads is the group of transformations that sends one of these triads to another triad. The TI group is called simply transitive on the set of consonant triads because there's a specific transformation in the group that transforms one triad into another specified triad. Now we're going to talk about something called Neo-Riemannian theory, which was pioneered by a music theorist and mathematician named David Levin. Neo-Riemannian theory introduced 3 ways of transforming the consonant triads, called the P, L, and R transformations. These transformations show up across history and across genres. Musical passages tend to consist essentially of these transformations performed consecutively on some initial triad. P, the parallel transformation, sends C major to C, A minor to A, and so on, swapping the parity of the triad. L, the leading tone exchange transformation, takes a triad, switches the third and the fifth, and then sends the root to the note which will swap the parity of the triad. R, the relative transformation, sends a major triad to its relative minor and a minor triad to its relative major. Note that the relative minor of C major is A minor because the C major scale shares all its notes with the A minor scale. The group of transformations generated by P, L, and R is called the PLR group. In their paper, Crayons and her collaborators show something fascinating. The PLR group is also isomorphic to D12. The PLR group is closely linked to a graph called the tonets, or tone network, which graphically relates the consonant triads. The nodes, or vertices of the tonets, are the pitches in numerical form. Transformations P, L, and R take consonant triads, which form triangles on the tonets, and flip them over an edge, producing another consonant triad, which shares 2 notes with the original triad. This provides a nice graphical representation of how combinations of P, L, and R can be used to map a consonant triad onto any other consonant triad. Musical passages tend to follow paths on the tonets as the harmonies shift and drive the passage forward. The most important revelation about the TI and PLR groups is that they are dual. This is a term proposed by Levin, and it means that they are each other's centralizers in the context of the group of all possible ways of transforming a triad. This means that the PLR transformations commute with the TI transformations and vice versa. You can perform a transformation from PLR and then a transformation from TI and get the same result as if you performed the transformations the other way around. Hopefully this video has made you feel like it might be worth doing a bit more investigation into music theory, group theory, or both. But if you take away anything from this video, let it be this. Group theory is a mathematical framework that gives insight into symmetry, and music is full of beautiful symmetries, so it's no surprise that group theory can be applied to music. Group theory helps give us a more abstract framework through which to view the features of music we've been making for centuries. Simultaneously, music gives us a more concrete way to think about the abstract concepts from group theory. In a sense, music and group theory share a portion of their own intrinsic beauties. There's a lot more that could be said here, and ways to relate music to group theory. People like Levin devoted their careers to the concept. I again urge you to read Musical Actions of Dihedral Groups by Crayons, Fiore, and Satyendra. For now, thank you for watching.